Welcome back to Hard Math with Kevin. I'm here with Kevin Mabe, the Chief Analytics Officer at Corus. We are in the third of our series on predictive analytics. In previous episodes, Kevin has shown us how to correctly set up a predictive analysis by looking at holdout data as well as the model data. He's then shown us a confusion matrix and how to look at that information. And in this episode, we're going to be looking at some of the actual robustness tests that he runs to determine whether the model that he's built is actually statistically robust or not. So with that, I'll put in the show notes, I'll put all of the links to the previous episodes. We'll also have this on our blog where you can download some white paper information if you so choose. Feel free to sound off and send us thoughts on what you'd like to see in future episodes. And with all of that, I'll turn it over to you, Kevin.
Yeah, thanks, Drew. So in the first video, we talked about the difference between this non-robust model and how this one is robust. And so what are the tests associated that we can actually, instead of just eyeballing it, what are the tests we can run in order to demonstrate that? In the previous video, we went through a categorical prediction example of 3 segments. And what are the tests we can run to show that the model performance on the holdout data here matches what we would expect on the model data. So this is essentially a summary of the tests that we run, and there's a lot here, but let's go through each one of them. So whether we are talking about a categorical prediction or a covariate prediction, basically like heights or incomes or things of this sort, something of a number nature. Underlying each one of these prediction for the categoricals is some kind of predicted probability. So the model basically said, hey, I got observation X, I'm about 60% sure it's a 1, I'm about 39% sure it's a 2, and about 1% sure it's a 3, so let's just call it a 1. So there are some predicted probabilities that underlie these values here. It is no different than showing, the general probability shape of the model data and the holdout data. So there's a chi-square test of distribution, and what that means is, does the mean of these distributions look the same statistically, and does the variance of these distributions look the same? Well, eyeballing this, it's obvious that they are not the same distributions, but we actually have a statistical test for that. In this example, we can actually demonstrate that the average of these distributions, as well as the variance of these 2 distributions, are in fact statistically similar. So that's a chi-square test of distribution. Now, we can also go further and impose not just overall, but for each category in a categorical model, does the underlying predictions match the model data and the holdout data? So you can do the same thing here. So that addresses the shape and the location of the probability distribution, basically the average and the variance. We also sometimes like to test the median because, as you know, with some data that could be highly skewed, for instance, this kind of data, the average is somewhere over here, but we like to measure a different central tendency, the median. And so there's actually a test that you can run to determine whether the medians of these distributions are the same as well. So it's just another additional test. So based on the mean and standard deviation of the variance and the median, you can run these different tests here. What we can also do for essentially just the categorical predictions is run a chi-square test on the distribution itself and a comparison of the adjusted count R-squares. And let me go back to this to show what this means. So based on all the actual segments and the predicted segments, we see that this confusion matrix has 9 combinations. Actual 1s predicted as 1s, actual 1s predicted as 2s, and so forth. So there's a distribution about how these observations fall in this 3x3 table. On the holdout data, the model fits in some way, and we have a similar confusion matrix. So the question is, statistically, is how this is distributed for the holdout data similar or different than how it's distributed for the model data? And so there are statistical tests, essentially a chi-square distribution that we can test for that. And you can also see that that already buys you a holistic understanding about whether these accuracies are statistically similar, whether these predictive values are statistically similar, and whether the hit rates are statistically similar as well, because these predictive values and these accuracies are dependent on the distributions of these tables. And one final thing is a Fisher's exact test for an adjusted count R-squared. Basically, that's a fancy way of saying how do we test whether this 36% is different than this 37%. It's just basically talking about two proportions. And so we want to be sure.
Named for Bobby Fischer.
Yeah. Champion, correct? Well played. Yes. Checkmate, my friend. Checkmate. But yeah, we can basically determine, is this reduction in the predictive error, basically the adjusted count R-squared, this 36% different than this 37%? So what we notice is that you get p-values for all these tests. We do not want to fail these tests. We do not want to show statistical evidence that the distributions are different. We do not want to show that there's statistical evidence that the medians are different. We also don't want to show any evidence that the distribution of the confusion matrix or the adjusted count R-squareds are different. And so we want these p-values to be essentially as high as possible. So high p-values essentially imply higher statistical robustness. But once you start getting these p-values below 0.05, 0.02, 0.01, 0.005, etc., you're starting to show signals of where the model is breaking down on the holdout data. And sometimes you can isolate it to one category if you're building a categorical model. But what that means is that you have to go back to the drawing board and say, hey, I built this model on the training data, and it's just not fitting the same way on the holdout data. So I may be overfitting some noise here. I may be too granular on some of my variables. I may be using too many variables. I may be using a weak variable that really shouldn't be there. And so try rerunning your models with fewer variables and just focus on the stronger ones. And likely what will happen is you'll start to fit models on your holdout data exactly as you expect on your model data. But until that happens, and until you can prove that you've passed or correction, you didn't fail these tests, you can't really demonstrate statistical robustness. If you can, then you can go back here and say, look, we approached the predictive analytics, we've held out holdout data, we built a model that fits the same way as expected, and we can actually statistically demonstrate that fact. And so not only did we build a predictive model instead of a descriptive one, we've built a statistically robust one.
That's great. Really, really interesting stuff. Well, Kevin, as always, thank you so much. This is incredibly helpful to our viewers. If you have any further questions, again, any ideas for future episodes or things that you'd like to see, please sound off in the comments or feel free to reach out to us. And as always, Kevin, thank you so much.
Hey, thanks again, Joe.